f prime, second derivative. I'm pushing my computer further. Okay. F of x and the second derivative. Okay. I will cross them out. Don't do that. I just need to make sure that I took care of everything. Okay. So f prime of 0 is 0. So at 0, f prime is 0. Also at 4 is 0. So this is taken care of. I don't have to cross it out. Okay. F prime of x is 1 for anything less than, for x less than -1. So -1 is here. So here it's positive because it's 1. And it is exactly 1. So the slope is 1 means that I have to show a straight line with a slope of 1. So it's positive, so it's increasing. Only a straight is it's a constant slope, so it must be a line. Okay, so this is taken care of. First derivative is positive between 0 and 2. Okay, so now I have to put a 2 in here. And I don't know what happens here. But between 0 and 2, they say it could be undefined, it could be something else. But I know that it's positive between 0 and 2. Done. Now it's negative between -1 and 0. It's also negative between 2 and 4. And it's also negative to the right-hand side of 4. So all this is taken care of. So I'm jumping over this for a second to go to the second derivative. Second derivative is positive. So of course this means that the function is decreasing here, is increasing here, is increasing here, is decreasing here, and it's decreasing here. Okay. And of course this is not a max-min because the first derivative does not change sign. Okay? Okay, so the second derivative is positive between -1 and 2. So positive between -1 and 2. And also between 2 and 4. Is that correct? I did find some mistakes in this book. So they said, just making sure, between -1 and 2, union 2 and 4. Okay, so something happens at 2, the function may not be defined. Okay. Do we have? Yes, we do have something about 2. Okay, got it. Just making sure. Okay, so again, something happens here. We're going to discuss that in a second. So also positive. So obviously, I can already make the conclusion that this must be a vertical asymptote. Okay, and then a positive also. Okay, so this is finished. And now it's less than 0 for greater than 4. Less than 0 for greater than 4. We have no information here because this is a straight line, right? Okay, so this is finished. Now, I'm coming back here. So the limit from the derivative as x approaches 2 from the left. So I truly believe that they didn't mean prime. That's why I left it so discussed at the end with you. So the limit from the derivative, so how does that look like? So the limit from the derivative function, which is a limit itself. So as x approaches -2 from the left. So obviously, if that's the case, then it's a vertical asymptote. On the left-hand side, we have positive infinity. And on the right-hand side, we have negative infinity. So I'm not sure whether they wanted the derivative, but obviously it must be a vertical asymptote. No other options here. Okay, so this point is definitely a local minimum. The function opens up. The derivative is 0. And also from the first derivative test, we know negative positive. This must be a local minimum. This cannot be anything because this first derivative does not change sign. Okay, so let's give it a shot. I summarize all that information. So let's take a look. So I need -1, 0, 2, and 4. -1, 0, 1, 2, 3, 4. So 2, 4, and -1. So before -1, the function is increasing, and it is a straight line. I can put whatever point I want in here. It doesn't matter. It doesn't say anything. I can make up whatever. Let me use a different color. I can make up whatever I want. So, but definitely has to have a slope of 1. I can make it a full point or an open point. We have multiple possibilities here. Here at 0, there is a local minimum. The function opens upward, and it's decreasing. So I'm going to make my minimum here. That's my decision, and I'm going to do this. And at 2 has a vertical asymptote, and it goes to infinity. So increasing, opening up, local minimum, goes to infinity, increasing to -1 as a straight line. You can start here if you want and do this. Or you can continue and make it continue from this point and make it continuous. It's up to you. We only need to use what we are forced to use, but the rest is up to us. Okay, on the other side, the function, well, let's take a look what happens here. At 4, it's always decreasing. It's always decreasing, but it's coming from -infinity. So on this piece, it's opening up. Between 2 and 4, it's opening up. I see, okay. Between 2 and 4, it's opening up. And then at some point in time, no, wait a second. If I consider this so the limit from the derivative, I'm still thinking of what they meant with this. So the limit from 2 to the left, it's going to infinity. So, which means that this is the tangent. To the right is going to -infinity. But I have that between 2 and 4, where is my 2 and 4? 2 and 4, it's still opening up. So if it's opening up, how can it come from -infinity? And at 4, so from 4, so the tangent here is 0. So I do have that piece, which is opening down, but here is opening up and decreasing. So oh, yes, yes, okay. Because I got it. Because it opens up, I don't have to connect them at all. That's up to you. So we can put a full point here and an open point here. And it is opening up, and the tangent is negative, yes. See, the tangent is negative. Tangent is negative, so negative and positive. It's going to positive and it's going to negative. So on this side, it's going to positive infinity. That's why it's this positive infinity for the slope, and this is negative infinity for the slope. Got it. So they really meant it. They really, now I see, they really meant it here. Got it. Once I graphed it, I realized what they meant by that. And that is correct. I don't need to put it here. We don't need to, but it's in this case, it's both infinities for our example. But now, once I graphed it, I realized why they put that in there. Because the slope here is positive, going to infinity, but the slope here is negative infinity on this side. Slope is negative infinity. On this side, the slope is positive infinity. That's what they meant. Now I got it. Very clear. When I graph it, I realized what they meant. And that's it. So this is an example. You can make other situations as you please. You can bring it here if you want. You can bring it here if you want with a minimum. Nobody says that we cannot add anything else, but we took care of everything they gave us. Very interesting situation. So that's what it is. Positive here, but negative here, and both towards negative infinity, which means the function itself goes to positive infinity, but on this side, the slope is negative, positive infinity, positive, and on this side, right here, the slope is negative. Good pick, thank you. That was good. That was a good example. Excellent. Whoever picked it deserves 5 points. Okay, so I think we can continue and go to a graphing. Would you like to choose anything else from here? Or we move on to the next section. This section is identical with 4.6. We're just adding a little bit more there with some asymptotes. Yes, I'm sorry, forgive me.
I would like another example.
Sure. Would you like to pick?
Sure. 60.
Okay, very good. So let's look at 60. For 60, since we had a rational function already, but it's fine. Let's do it. X squared minus 4 over x squared plus 4. I wanted to show at least one type of each, a different type. But if you picked 60, maybe you picked it for a reason. Okay, let's do it. So I look at 60, and the first thing I do, it has to be this. And I realize that this function has what domain? Can anyone identify the domain for us? Can anyone give us the domain? Anyone, please?
Is it negative infinity to -4 and
Careful, careful. X squared plus 4 can never be 0, no matter what you do. A positive plus a positive can never be 0, right?
yes.
Good. So can anyone give us the x-intercepts? We have to set the function equal to 0. When is a fraction 0?
Or when the numerator is 0.
Very good. So then x plus or minus 2. So -2, 0 has to be in the middle, and 2. Okay, so 0 for the function and 0. Can anyone plug in 0 and determine for us f of 0?
-1.
-1 indeed. Good. The other thing I need are these limits, and I'm done. I'm done with the function. I have x and y intercepts. I have the limits and a symmetry in a minute. Okay, so can anyone tell us what to do with this? How do we proceed? How do we determine this limit? Where does the numerator go? Now you see all this is coming from the previous chapters. The numerator is infinity, the denominator is infinity. So what do we do then? What is the method in this case?
L'Hopital's.
Very good. So the top prime is?
No.
Just the top.
So 2x.
Good. What about the denominator?
2x.
Good. So what is the limit then?
1.
That's it. And 1 is a horizontal asymptote. 1, 1. There is no, I did not use the negative or positive, so it must be on both sides. So then y equals 1 is a horizontal asymptote. Good. Now let's talk about symmetry. It's very important. So let me refresh your memory on symmetry. Odd functions, so symmetry. Symmetry. Odd functions. F of negative x is the opposite of f of x. For even functions, f of negative x equals f of x. In both situations, we have to determine f of negative x. So let's do just that. So remember, will this change if I plug in negative x? Will this change if I plug in negative x?
No.
No. So this is the situation. F of negative x equals f of x in our case, and the function is even. So this is the only thing that I have to add somewhere else in the table, or above or below. So even function, so I don't forget. Even function means the function is symmetric with respect to the y-axis. Here's an example. X squared. X squared is symmetric with respect to the y-axis. X squared is even. Okay,